So this all leads us to section 6.7, which is on solving equations using the zero product rule. So first we notice that, I think I've used this term before, a quadratic equation is an equation, that has a polynomial of degree 2 equal to 0. And so in general we can say ax squared plus bx plus c equals 0. And so you notice that if we said x squared plus 4x plus 3 equal to 0, that is a quadratic equation. We're also interested in what we call the zero product rule. This just lets us know that if a times b equals 0, then a equals 0 or b equals 0. So it's fairly intuitive. It's basically just letting us know that there's no magic pair of numbers that isn't 0 that can have product of 0. So we can't say 2 times negative 5 equals 0. We can't say the square root of 7 times the square root of 19 is 0. We know that if a times b is 0, either a is 0 or b is 0. And so this is really convenient compared with our factoring, because we know that if we wanted to solve x squared plus 4x plus 3 equal to 0, all we have to do is factor, set the factors equal to 0. So we notice that we can look at this as x plus 1, x plus 3 equals 0. Then we can say x plus 1 equals 0 or x plus 3 equals 0. And so we can solve each of those individually, subtract 1 from both sides, subtract 3 from both sides. We find out that x is negative 1 or negative 3. And you notice that some of these you can solve just by looking at them. We notice we look at x plus 1 times x plus 3, that'll be 0 if x is negative 1 or x is negative 3. There'll be some that we'll have to work a little bit harder at. So if we tried something like 4x squared minus 11x equals 3, we notice this isn't in the correct format yet. You notice it's not set up as a quadratic equation. We know it can be. We can subtract 3 from both sides. We're going to get 4x squared minus 11x minus 3 equals 0. And now we can factor. We know 4 times negative 3 is negative 12. We know 1 times negative 12 is negative 12. 1 plus negative 12 is negative 11. And so we can factor that as 4x squared minus 12x plus x minus 3 equals 0. Then we can plot a factor of 4x times the quantity x minus 3 plus 1 times the quantity x minus 3. Remember, we can always pull a 1 out. And so we discover we have the quantity 4x plus 1 times the quantity x minus 3 equals 0. And so we can say 4x plus 1 equals 0 or x minus 3 equals 0. And again, the question of how much algebra you have to put into this depends on practice and personal preference. We notice that we can just look at this and say x is negative 1/4 or positive 3, but we can also work it out. We can subtract 1 from both sides. 4x equals negative 1, divide by 4. We get x equals negative 1/4. We can add 3 to both sides. X equals 3. And so if a value of x that makes the equation true is obvious, go ahead and use it. You'll notice that sometimes they'll be really obvious, other times they won't be as obvious. It's just the way it goes. We have to be careful. Sometimes things won't be arranged quite the way we'd like. If we had something that looked like 3q times the quantity q minus 3, is equal to 12, we notice that we can't just say, 3q equals 12 or q minus 3 equals 12. This won't work. We notice that would give us q equals 4 or q equals 15, and you notice q equals 4 would work. Q equals 4 is a solution. Q equals 4 works. Q equals 15 doesn't. You get 45 times 12 is going to be something like 240, which is not 12. What we can do is multiply it out. We get 3q squared minus 9q equals 12. Subtract 12 from both sides. We get 3q squared minus 9q minus 12 equals 0. We notice that we could either factor a 3 out or divide both sides by 3. We could have done division by 3 at the start. Turns out this is going to be the same thing as q squared minus 3q minus 4. And so now this is an easy factorization. We're going to get q minus 4, the quantity q minus 4 times the quantity q plus 1 equals 0. And so we find out that q minus 4 equals 0 or q plus 1 equals 0. And so we get q equals 4, or we can subtract 1 from both sides. Q equals 4 or q equals negative 1. Let's make sure we've got that written right. Yeah, q equals 4 or q equals negative 1. So one interesting trick is that you'll notice that the degree of the equation lets us know how many solutions we could have. So we notice that quadratic equations are degree 2 have polynomials of degree 2, so have at most 2 solutions. They can have fewer. We notice if we looked at x squared plus 4 equals 0, we notice that that has no factorization. Basically, we're saying x squared equals negative 4. There is no value of x that makes that true. This has no solutions. And if we had something like x squared plus 4x plus 4 equals 0, we notice that's going to be x, that's a perfect square trinomial. We get x plus 2 quantity squared equals 0, and so we get x plus 2 equals 0 or x plus 2 equals 0. And so we know we can subtract 2, x equals negative 2, and so this one has only one solution. And so we notice that if we've got that polynomial of degree 2, we know that once we have 2 solutions, we know we're done. There aren't any more. And again, we can have some quadratic equations that will have no solutions, some that will have only one solution. That can happen from time to time. Something else to look at is if something was already factored for us, if we had something like x times x minus 3, x plus 3 equals 0, we notice that this is already, most of the work is already done for us. We know that either x is 0 or x minus 3 is 0, or x plus 3 equals 0. And so we know that we can add 3 to both sides. X equals 3, subtract 3 from both sides. X equals negative 3, or obviously x should be 0. So we have 3 solutions this time, and you notice that if this had been written as a polynomial, we could have written it as x times x squared minus 9 equals 0, or as x cubed minus 9x equals 0. So you notice that polynomial x cubed minus 9x equal to 0, that equation has 3 solutions, which is reasonable because it's degree 3. The polynomial is degree 3, so we're going to have up to 3 solutions. We'll try one more that's a little bit trickier. If we try looking at 3z, z minus 2, so if we had 3z times the quantity z minus 2, and then we subtracted z, and we set that equal to 3z squared plus 4, this one is not obvious. So what we have to do is first multiply everything out. We get 3z squared minus 6z, so that 2, that's a minus 2, that's better. So we have 3z squared minus 6z minus z equals 3z squared plus 4. So now we can subtract 3z squared from both sides, subtract 4. And so we notice that the 3z squared minus 3z squared is 0, negative 6z minus z is negative 7z, minus 4 equals 0, and so in this case, no factorization. We can just add 4 back to both sides, get negative 7z equals 4, divide by negative 7, and so z is negative 4/7. And we notice that we're not obligated to get integer solutions, we're not obligated to get rational solutions. So that's one of those things where we can easily have rational solutions, we can easily have irrational solutions. And that's something we might talk about more in later chapters. We actually notice that we can have all sorts of solutions. If we had x squared minus 5, whoops, if we had x squared minus 5 equals 0, we notice that we don't have a nice factorization, but it turns out we could say x minus square root of 5 times x plus square root of 5 equals 0, and so we could say x equals square root of 5 or negative square root of 5. And we'll talk about that more in a later chapter. We're not ready for that just yet. But it's a nice example of having 2 solutions that are literally irrational solutions.